All right, welcome everybody to a video code lab tutorial as part of our machine learning course. Today, students are tasked with plotting out a linear relationship between randomly generated data points, and we're going to be using the NumPy library and some special methods to achieve a best fit line. So that is achieved using what's called the least squares methods. And students should have, excuse me, as part of this tutorial, both PowerPoint lecture materials. So the least squares method and the slope intercept form that we've covered in a previous class, and you can find that inside module 3 there. Okay, just inside our linear regression folder. Okay, so have those open because we are going to reference that. And let's get started. So I'm going to open up a command prompt. Again, some students may have to just open up Anaconda and then just launch Jupyter from the Navigator dashboard. Okay, so that opens up a file directory. I'm just going to make sure this file is saved on a new inside the desktop rather, or if you have a folder that where you're saving your projects, that works too. Okay, and we're just going to create a new notebook, Python 3 kernel, and we're going to open that up. You can name it. Let's go linear regression code lab, and then I would just put your name on it. Okay. Because when you do go to submit it through Blackboard, it's already on the file and easily identifiable. Okay, so let's get started. So first things first, we're going to import NumPy and give it an alias as NP. And then we are, part of this is a visualization, so we are importing the PyPlot module. And that's part of course, matplotlib. Okay, so we have that. And this code lab is actually pretty simple, but it gives us some good insight into how things work as far as making these linear regression predictions, perhaps the most basic or simple predictions that we've seen so far. And so what we're going to start with is we could, for instance, create an array manually or a list or a vector manually, but we're going to create some synthetic data just using NumPy's random method, okay? So we're going to start by generating some random data points, okay? And we're going to go np random seed. If you recall from, actually, you know what? Let's set that to 0. If you recall from prior instruction or prior classes, that ensures that the data points do not change every time you run the code blocks. If you provide a seed, the randomizing function will stay consistent so you can observe the data, okay? All right, so we've set the seed. The next step is we're going to go np random rand, whoops, I had that in a comment, and we're going to give that a value of 50, so it's going to give us 50, and then we're going to times it by 10. So what this is doing is this rand method gives you uniformly distributed, I would say, pseudo-random numbers, okay, because they're not true random numbers. And what this means, the rand function will just give you numbers that essentially are uniformly distributed meaning they're not clumped closer to 0 or closer to the ceiling there or in the middle. We want a nice uniform set. Okay, we're going to actually give this a variable or equal that to a variable, in this case x, which is in machine learning models, x is always the input, okay, where it is the independent variable. It could represent a feature as well, okay. All right, so let's inspect this, and we can just write print, but we're going to have a string value just indicating what it is, okay? And whenever we want a string value, we enclose it in double quotes, and then we have this little comma here, and then finally the variable. So if you go ahead and run that, you can see we have our numbers there. Okay, and that should be 50, and you can see these values are uniformly distributed, okay? It gives us a good cross section. All right, great. So NP random rand, we set it to 50. If you want to find out more about this rand method, you can just hover over it and hit Shift Tab, okay? And we can read the documentation inside the Jupyter notebook, okay? All right, so random values in a given shape, okay? All right, let's see here. Okay, so they have an example. So 3 by 2, and you can see there's 3 rows and there's 2 columns, okay? All right, pretty simple there. Okay, so let's keep going. The next thing we're going to do, so we have x, we have the data points for x. Now we need our outputs, or our targets, and that's symbolized by y, okay? And y is going to work a little bit differently because we need to simulate output values that are variable and kind of synthetic real-world data, okay? But the y, if we go back to our slope-intercept form lecture, the y in this equation, the slope-intercept form, is equal to the change of x, or the percentage change of x, plus b, which is the y-intercept, or the starting point. So y in itself can't be defined. Y is defined by this change of x plus b, okay? So how do we represent that here? So let's go, and we want to take on that slope-intercept form. So we have 2 times x, okay? 2 times x plus 1 plus np random. And instead of, if you recall, we use rand up here, we're going to use rand n. And we'll just explain the difference between the two in a second. Excuse me. All right, so y now is this change of x, or the rate of change. So for every x change, y is going to change by 2. We're going to plus it by 1. Okay, so that's kind of like the increment. And then we're also going to introduce this noise, which is also times by 2. So we have 50 points here. And the rand n function actually gives us, instead of uniform data, it gives us data that is a normal distribution. Okay, so normal distribution. And what that means is it falls on a Gaussian or bell-like curve. Okay, just like in our examples where we let's just liken it to the bell-like curve, where we have the example of IQ scores along a normal distribution. Well, we know most IQs will stand or fall in the middle, or the average. So these numbers are going to be closer to the mean. Okay, most numbers are going to fall in the mean, and that's what normal distribution means. Okay, the mean is 0 and the standard deviation is 2. All right, so what does this look like now that we've set this up in slope-intercept form? Well, let's output the y now. Okay, so make sure we have that comma, otherwise that will not work. And sorry, put the colon inside the double quotes. Okay, so if you output that and run it now, we have our x on top, and now we have the y. Okay, and these are more uniform, normal distribution for the y, and then the x is uniform distribution, so we get a more scattered, I would say, sample of data points, where y is the numbers are falling mostly on the standard or normal distribution, okay, or a Gaussian curve. Okay, all right. Okay, so remember, x is our input values, okay, our independent variables, and y are our target values or output or dependent variables. So again, we know is y is dependent because y is made up of this change in x plus 1 plus this random noise. Okay. All right, so hopefully that's making sense. And all you have to do is go back to our lectures and say, okay, well, we know y, the output, is composed of the slope, which is the rate of change of x, plus this b, which is the starting point or the y-intercept, okay, on the coordinate system. All right, so hopefully that's making sense so far. Okay, and we've been introduced to two random methods. And again, you can inspect those methods pretty easily. Okay. All right. So this next part is, now that we have x and y defined, is we're going to use NumPy's what's called polyfit method or function. I'll just refer to it as method to perform linear regression on given data points. So the data points x and y. Okay, and what this polyfit method or function does is it takes x and y, and then there is a third argument, and we'll just note this, which we set to 1, indicating that we want to fit a polynomial. So a polynomial in the degree 1. So what does that mean? So a polynomial is, it represents a linear function where its terms have exponents, or its coefficients have exponents no greater than 1, okay? And that actually represents a linear function, okay? So we use NumPy's polyfit because what it does for us, and if we go here to our least squares method, is it automatically determines this best fit line based on these equations here. Okay, so what it's really determining is it, and if we read the description here in the comments, it minimized the sum of the offsets. So if you look at these data points at this best fit line, we're looking at these lines. That's the offset. Okay, how far apart are they from this line? This line would represent our predicted values, and these data points represent actual values. So we compare the two, we get the residuals or the offsets. It's called least squares because we do square these offsets to just represent the data or scale the data so differences are more pronounced, and that's why we square it. And this method helps us plot the best fitting line, okay? But we need to supply things like the the m, which is the slope, and the beginning, or the b, the y-intercept, okay? So hopefully that's making sense. So this polyfit method is going to help us do that. So first, we're going to define some variables. And here we just use chaining. So we have two variables, and this is going to be equal to np polyfit. Whoops. And we're going to give it x as the first argument, y, and then this first degree, because it represents a polynomial or linear function where exponents go up to 1. Okay. All right, and you can go ahead and shift tab this function and just look at the parameters. You can look at the different ways you can use it, and just find out more information, and you can see the term polynomial right in there. Okay. All right. So this actually returns our slope and intercept respectively, just like so, and that's why we have it laid out like that. Okay. So let's continue now. So with this information, we can plot our best fit line. And now we are going to invoke the use of matplotlib. So we're going to plot the data points and the regression line, or the best fit line. Okay. And we've done this before, so of course we can use bar plot. We've created synthetic or random data, so we're always going to use a scatter plot to represent that, or a scatter graph. And we're going to give it a label of data points. Okay. All right. Okay, so in this scatter, we just have the x and y values that we've already defined above. The next part is this plot. Okay, so how do we plot the data? So we're going to put in x, then we're going to put in the slope, which is m, right, the rate of change, times x. Okay, just like, why do we times it? Well, m times x in our slope-intercept form, right? As the second argument here. But we're also going to include the intercept because we need the starting point. And so here we're just mimicking x and y. So y is composed of this equation here, the slope-intercept form, and that's exactly what it is. And the polyfit method gave us those variables from our data. Next, we're going to give the line a red color. So this is actually the line, and we can give it all sorts of colors, and we're going to name it regression line accordingly. Okay, so polyfit, as you can see, we have x values, and then we have our y, which is, again, that slope intercept form that we've returned from the polyfit method. And that does that. Again, this method abstracts away the least squares calculations, so we don't have to do it manually. We just plug in these arguments, okay, making it nice and easy. Next, we're going to go plot x label, okay, and this is just a string value, x, and plot y label, and y, okay, and we're going to give it a title. We're going to give it linear regression, and we're just going to include a legend, and we're also going to show a grid, and we just pass in that bool to true, and then finally the show. Okay, And that's it. So the matplotlib implementation is pretty simple. We've already dealt with the seed method and a random or synthetic number generation. We really just wanted to hone in on the slope and y-intercept, and that pairs well with our recent lectures. So if you want to know more about this, or if it doesn't make as much sense, there's 2 lectures there explaining the least squares method and the slope intercept form. Okay, so let's run. So first we get the xy. Okay, so we printed those values. But now we get our visualization with the best fit line. Okay. Okay. And so this line represents, through the least squared method, the best predicted values if for a given value of x that you input into this linear regression model, I would say. And we can even print out things like slope. Let's print the slope out. And let's also print the y-intercept, or the b part of that equation. And again, these are outputs from the polyfit math function. Okay, and we can see the slope, so the rate of change. So y is equal to the change of x, okay, times this, okay, plus the starting point, which is the y-intercept. And you can see when you see a b value or a y-intercept value of close to 0, it just means you can pretty much call it 0, okay? But you can see it's just slightly above that 0 if you were to intersect with the y-axis, okay? So now that we have our best fit line, if we're operating on the assumption, and this is key, we assume that x and y are correlated strongly, okay? That's the assumption. If we don't have that hypothesis, then this doesn't make sense. It breaks down, right? So you have to be careful about these assumptions, and you can run the correlation coefficient on these 2 variables. This is a binary problem or a bivariate problem where you have 2 variables, okay? But this is operating, again, under the assumption that x and y are closely linked, or they have a strong relationship or correlation, okay? Okay, so we have our best fit line from the data set, but what happens now if I want to predict a new value or new input or a new x, okay, along this line? I want an accurate y output or prediction, okay? So how do we do that? So let's go down below, and we're going to generate a new x value or input for predictive purposes, okay? So we're just going to say new x is equal to 7. Okay, so that's our input, and we want to get a corresponding output based on prior data, and that's the whole point of these linear regression tasks. Okay, so we're going to predict, we're going to predict the corresponding y value using, using the best fit line equation, the slope-intercept form. So that's y equals the change in x, or the slope times x, or the input, plus b, which is the y-intercept, or the starting point, okay? And we're just going to map that out now. So predicted y, because we know at this point that y is composed of this change in x. So we're going to go m times new x plus c, okay? We're just going to call the b c this time, okay? Sometimes, depending on, if it's stats or machine learning or other notations, this equation can appear differently, but just know it's the same form, okay? All right, now we're going to print just a string here. So for x equals, okay, comma, new x, and then we're just pretty much interpolating a string here in this print method. So the predicted y value is colon, then we, after every double quote, we have to have that comma, and we're going to go predicted y, okay? All right. Make sure you have that. And now we're going to plot the original data points and the best fit line, just like we did above, because we're in a new code block, so we have to kind of replicate things. So we're going to go scatter plot again, and we're going to provide the x and y values, and that's label data points. Okay. The next point is, or the next statement here is the plot method, and we're going to do pretty much the exact same as we did in the prior code block. We have the slope-intercept form, so slope times x, or new x, plus c, okay? Sorry, don't put new x, just have the x in there, okay? But that's what we're going to do, and color for the line is going to be red. Sorry, that should be lowercase. And just like up above, we're going to give it a label, best fit line. And these are named arguments or keyword arguments in Python, okay? It's part of the plot method. All right, so the next part is we're going to plot the predicted point. So we want this point to be unique just because it is our input, and we don't want it blending in with all the other values like up above. Otherwise, it doesn't give us an indication of anything. We can't really make the visualization. So we're going to have another scatter. And this time, instead of x, we're going to have the new x, and we're going to have the predicted y rather, and we're just going to give it a distinctive color green and its own label, okay? Whoops. Predicted point, okay? So we want to differentiate between, and if you run, why is this not running? Okay, so probably a good time to save that if it's not running for you. Okay, and I just hit that randomly. It still needs the show function in order for this to work, okay? So we're going to go plot x label, and basically we can just copy this stuff from up above. We don't have to write it again. So up in the prior code block, just copy that stuff. And looks like I have just some errors here, and I'm just going to determine what those errors are. Okay, so it's saying m is not defined. All right, so whenever you see that, I'm just going to run all the cells. Okay, so m is not defined. Let me just troubleshoot that. Did we define m in the prior code block? Well, it should be the slope. Should be the slope. Just give me 1 second, everyone. Predicted y. So I don't believe we have defined M, but let's see here. Well, perhaps we could borrow that from okay, let's try, since we've all right, now C is not fine. Okay, let's do C is equal to intercept, and you know what? I'm going to change that to B, because I want everything represented as a familiar form. Okay, so if we go back to the lecture, I want it looking like that so we can tie it in nicely. Okay, perfect. Okay, so just make M equal to slope, B equal to the intercept, and these are defined by this polyfit method up above, and we get this best fit line, which represents the best fit line up above. Let me just hold on, because this is not running, so I just want to okay, I'm going to open up a notepad here. Okay, I'm just going to have that handy. And I just want to go, whoops, got to be careful here. I don't want to delete everything. Okay, so I just had to cut and paste that and delete that cell because it wasn't working. Because basically we get the same linear regression plot. But here we have a new x input, okay? And that's why we printed it out like so. And what it says, based on our best fit line, so these, again, in the least squares methods, when they say we're summing the difference and we're squaring the difference between the predicted values and the actual values, well, these dots, these data points represent the actual, and this line the best fit line represents predicted, okay? So for x, if it's equal to 7, and if you recall, that's our new input, x, y will be equal, and we could just line this up. So if we find 7, which will be middle here, we go up to this red dot, or green dot, I'm sorry, I'm colorblind, and if we line it up with the y-axis, we should get a value of, if it's 5, somewhere around 14, right? Based on our best fit line. And sure enough, we get 14.5. So now we can predict output values or target values based on input, or x. Okay, and it's just that easy. We can visualize it now. And now we know the internal kind of mechanisms of the code and how this is working. So I'm hoping students understood or enjoyed that. Again, please go over these lectures, least squares, and the slope and intercept form. But that's it for the Code Lab. Thank you again for watching, and we'll see you next time.